Hello, welcome to 3.5, limits at infinity. Consider the function f of x equals 2x squared over x squared plus 2. What is the end behavior of this function as x gets really big? If we graph this function, we get this kind of shape for x between negative 5 and 5. It appears that the end behavior is leveling off, so let's look at as x gets larger. So in this graph, we see x being between negative 50 and 50. So this appears to be leveling off at y equals 2. Might expect that, 2x squared over the x squared there. So if we examine this in the table, you can see these values. As x gets really big, it gets closer and closer to 2. So the table suggests that the value of f of x approaches 2 as x increases without bound. Similarly, f of x approaches 2 as x decreases without bound. So the limits at infinity are denoted by the limit as x goes to negative infinity of f of x is 2, and the limit as x goes to infinity of f of x is 2. So the definition of limits at infinity, let L be a real number. The statement limit as x goes to infinity of f of x equals L means that for each epsilon greater than 0, there exists an m greater than 0 such that f of x minus L is less than epsilon whenever x is bigger than m. I know you probably thought like I did, I hoped, that we were done with the epsilon delta stuff, but it's here for the definition. The statement limit as x goes to negative infinity of f of x equals L means that for each epsilon greater than 0, there exists an n less than 0 such that f of x minus L is less than 0 when x is less than n. So horizontal line y equals L is a horizontal asymptote of the graph of f if the limit from either direction is going towards L. Let's go on to the next page. So limits at infinity. If r is a positive rational number and c is any real number, then the limit as x goes to infinity of c over x to the r is 0. And if x to the r is defined when x is less than 0, then the limit as x goes to negative infinity of c over x to the r is also 0. So in example 1, we want to find the limit as we go to infinity. So if we multiply by 1 over x cubed from the denominator, we multiply this by 1 over x cubed over 1 over x cubed. We have the limit as x goes to infinity of x squared over x cubed plus 2 over x cubed over x cubed over x cubed minus 1 over x cubed. This be the limit as x goes to infinity of 1 over x plus 2 over x cubed over 1 minus 1 over x cubed. So if we apply what we just saw, this becomes 0 plus 0 over 1 minus 0, which is 0 over 1, which is 0. So our limit as x goes to infinity of x squared plus 2 over x cubed minus 1 would be 0. Now let's look at the next one. We have a limit as x goes to infinity of x squared plus 2 over x squared minus 1. And you might be able to guess this if you remember your work from pre-calculus. You're going to do 1 over x squared. That's the biggest power on the denominator. That's going to be the limit as x goes to infinity of x squared over x squared plus 2 over x squared over x squared minus 1 over x squared. That's going to be 1 plus 2 over x squared over 1 minus 1 over x squared. That's going to be 1 plus 0 over 1 minus 0, 1 over 1, which is 1. So our limit, excuse me, as x goes to infinity of x squared plus 2 over x squared minus 1, it's going to be 1. Feel free to pause it if you need to. So guidelines for finding limits at plus or minus infinity. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients, as we just saw in the second part. if the degree of the numerator is greater than the degree of the denominator, the limit's infinity. It does not exist. So determine the limit of, as x goes to infinity, negative infinity of 2x plus 1 over the square root of x squared minus x. And note for this one, for x being less than 0, x equals negative the square root of 2, the square root of x squared, because we're on as x goes to negative infinity. So you might be able to guess just by looking at this. You see 2x on top. Down here, square root of x squared is x. So from that, you might guess it's 2. Let's work it out and find out. So we have, I'm going to scroll this up to give me more workspace. Multiply by 1 over x. We have, multiply here, 1 over x over 1 over x. That's the limit as x goes to negative infinity of 2x over x plus 1 over x over the square root of x squared minus x over x. And I think I'm supposed to do, I'll leave it like this for now. That's going to be 2 plus 1 over x over square root of x squared minus x over x squared. The square root of x squared is x. So we have the limit as x goes to negative infinity of 2 plus 1 over x over the square root of x squared over x squared minus x over x squared. That's going to be 2 plus 1 over x over the square root of 1 minus 1 over x. So now as we apply our limit, it's going to be 2 plus 0 over the square root of 1 minus 0. It's 2 over the square root of 1, which is 2. And I think I need to treat this as, right here, when I brought this in here, call this negative. As we just saw right there. So it's negative here, negative there, negative there, negative there. It's negative 2. So our limit as x goes to negative infinity of 2x plus 1 over the square root of x squared plus x is negative 2. Okay, for the next one we have, we're going to find the limit as x goes to infinity of sine 2x over x. So first recall that negative 1 is less than sine it, less than or equal to sine x, less than or equal to sine 2x, I'll even call it, less than or equal to 1. So if I divide both sides by x, negative 1 over x is less than or equal to sine 2x over x, less than or equal to 1 over x. Now the limit as x approaches infinity of negative 1 over x, that's going to be negative 1 over infinity, which is 0. And the limit as x approaches infinity of 1 over x is going to be 1 over infinity, which is 0. So, by the squeeze theorem, the limit as x goes to infinity of sine 2x over x is also going to be 0. So just imagine the one curve looks like this, the other curve like this, and here's that sine in between. Yeah, don't need that. We're going off to infinity. I'm going to go on to the next page. Okay, engine efficiency. The efficiency of an internal combustion engine is 100 times 1 minus 1 over V1 over V2 to the C power, where V1 over V2 is a ratio of uncompressed gas to the compressed gas, and C is a positive constant dependent on the engine design. Find the limit of the efficiency as the compression ratio approaches infinity. So here our limit as V1 over V2 goes to infinity of 100 times 1 minus 1 over v1 over v2 to the c power. It's going to be 100 times 1 minus 1 over infinity to the c power. 100 times 1 minus 0, which is 100 times 1, which is 100%. So let's go for a 100% efficient engine, but to do so, our compression ratio has to be infinity of the uncompressed gas to compressed gas. It's not going to happen. Most internal combustion engines are about, I think, 23% efficient. That means the energy that goes into them, 23% is turned into power to move the vehicle. Okay, let's go on to definition of infinite limits at infinity. Let f be a function defined on the interval from a to infinity. The statement the limit as x goes to infinity of f of x equals 0, f of x equals infinity, means that for each positive m there's a corresponding n greater than 0, such that f of x being bigger than m whenever x is bigger than n. And the statement the limit as x goes to infinity of f of x equals negative infinity means that for each negative number m there's a corresponding n bigger than 0, such that f of x being less than m whenever x is bigger than n. Okay, example 5. So sketch the graph of the equation. Look for extrema, intercepts, symmetry, and asymptotes as necessary. So here's the graph of it from the calculator. And if you look at this, x over x squared minus 4, x squared minus 4 equals 0 means x minus 2x plus 2 equals 0 means x minus 2 is 0, x equals 2, x plus 2 is 0, x equals negative 2. So our asymptotes are at 2 and negative 2. So those are our vertical asymptotes. It's x over x squared, so if we take the limit as x goes to infinity of x over x squared minus 4, that's just going to be 0, because the rule of the power on top is less than the power on bottom. So y equals 0 is the horizontal asymptote. We have this one, and this one, and a horizontal asymptote. What else they want? Extrema. We don't have any extrema. Intercepts. So y equals 0 means x over x squared minus 4 equals 0. That occurs whenever x equals 0. So there's only one intercept right there. 0, 0 is the x-intercept and y-intercept. How about symmetry? Think of negative x. Y equals negative x over negative x squared minus 4. That's going to be negative x over x squared minus 4. That's not the same as the original. That is the opposite of the original. So that means this is an odd function. So it has symmetry with respect to the origin. There are no extrema. I mean, the first derivative is going to be negative x squared minus 4 over x squared minus 4 squared. That means negative x squared minus 4, the numerator equals 0. It means negative x squared equals 4, or x squared equals negative 4. That's not going to be real. So Okay, that'll do it for that problem. One more page to look at. One on the last page. Feel free to pause if you need to. Use a computer algebra system. I'm using my 89 to analyze the graph of the function and label any extrema and or asymptotes that exist. The graph is down here, so I'll move it up in a moment. Looking at f of x equals x over x squared minus 4, same graph we just saw. As I said before, f prime of x was negative of x squared plus 4 over x squared minus 4 squared. And our second derivative, f double prime of x, is going to be 2x times x squared plus 12 over x squared minus 4 cubed. If you want to see me work those out, I mean, you can see all this stuff worked out here. And in the notes I did from 2011 I did those. 2010. So based on this information, I mean, right here there's not going to be any extreme values that we discussed in the previous example. From here, 2x equals 0 when x is 0. X squared plus 12 equals 0 means x squared equals negative 12 means x equals plus or minus 12. Square root of 12. I times the square root of 12, not real. So we only have one value to really consider here, x equals 0. So if we go negative infinity to 0, well, we have the asymptotes too. Let me bring this graph up a little bit. So we have, this was again negative 2, this is at 2, here's 0. So our intervals are going to be negative infinity to negative 2, negative 2 to 0, 0 to 2, and then 2 to infinity. Let's get a test value. How about negative 3, negative 1, 1, and 3? So look at f double prime of x. We'll put negative 3 in here. Because 2 times negative 3 is going to be negative 6. That part's going to be positive. Down here, negative 3 squared is positive 9. 9 minus 4 is positive. So that's positive here. Negative 1. 2 times negative 1 is negative 2. Sorry, it was negative over positive. That's negative there. And this negative 2 there, that's going to be positive. So negative 2 on top, negative on top. Do negative 1 squared, that's going to be negative 1 squared is 1. 1 minus 4 is negative 3. Negative 3 cubed is negative. Negative over negative is positive. Putting 1 in here, you get 2 over the negative. That's negative. Putting 3 in there, you're going to have positive over positive. That's positive. So our conclusion here, concave down. Concave up. So here's concave down. We see that, looks concave down. This does look concave up. Then at that turning point right there, at this inflection point, it goes to concave down. So that 0, 0 is an inflection point. And then from 2 on, it's positive, so it's concave up again. So we have concave up, concave down, and inflection point. So it's concave up from negative 2 to 0, and then from 2 to infinity. And then from negative infinity to negative 2, and then 0 to 2. That'll do it for 3.5. That's limit at infinity. Send me your questions. Thank you.